All right, so the tests are graded in. The average is about an 81, which is not bad for as terrified as the faces I saw when we were leaving. So, just like please don't leave things blank, and especially don't leave questions blank if I can see the ghosts of answers past where you have erased stuff and then left it blank. That is choosing to get 0 points. If you try, I can always find something. Otherwise, if you leave it blank, you are choosing to get 0 points because I can't give you points for the ghosts of a thought. So don't leave me ghosts. Actually answer. Leave things up there. Okay. So we're going to be moving on to Unit 2. Fresh start. On the table when you came in was the schedule for the whole chapter. It gives you all the homework problems, gives you what days we're doing what. So if you didn't pick it up, pick one up over there. Again, all the homework problems, the date we're doing it, all up there. The dates of the quizzes, the date of the chapter test. This is going to take us right up to fall break.
The days that we're losing our minds.
So this is the plan.
I keep forgetting that I have
If you have a study hall, you can come in here and do that. Or we can do 5th period, like in that extra study time, or I'm after school today until 3:30. So any of those options. Yeah. Yeah. And then I can write you past if it takes more than 1 day. Yeah. All right. So we are going to be starting to talk about functions and doing some graphing. You don't need like a full proper graph on this. If you just put like the axis on this, we don't need like a full grid. When we get into actually graphing stuff on coordinate planes, I will give you guys graphs. I have piles and piles of them. If you ever need graphs for things like homework, I have a vast variety of very small graphs here. I have straight up graph paper down here. So you're welcome to take any number of copies you need of any kind. If you need little graphs, you need big graphs. I will provide graphs. You don't have to have graph paper. If you want to have graph paper, if you want to have a graphing paper notebook, like you can. I will give you graphs and scissors and glue when we get to them, and that to actually plot up points. But we're going to start by remembering some things about the plane, the coordinate plane. So first things we need to remember is which quadrant is which one. They all have names. I say names. I mean like 1, 2, 3, 4. So which quadrant's number 1? Let's start with that. Top right, positive, positive. So this guy is quadrant 1. When my x values are positive and my y values are positive. So x values, y values. Both x's and y's are positive. That's quadrant 1. Quadrant 2, we go this way. So when we're counting, we go around counterclockwise. So quadrant 2 is going to be this guy over here. We typically use Roman numerals, but it's not that big a deal. Quadrant 2. And in this case, my x values are going to be negative and my y values are going to be positive. So if I get a negative x and a positive y, I know it's going to be in quadrant number 2. This is again my x values and my y values. So this quadrant down here is which one? 3. 1, 2, 3. Schmerp. Again, we use Roman numerals just kind of out of tradition, but if you call it quadrant 3 with a numeral 3, I know what you mean. It means the same thing. And in this case, we know we're going to have negatives in both. Negatives and negatives. Negative x's, negative y's. And then our last quadrant over here, quadrant 4. I have no idea why I slanted the 1. That was weird. Nope, it does count around as a circle. It goes in a loop. And here we know that our x's are going to be positive, but our y's will be negative. So it goes in a circle like this, kind of counterclockwise. We're going to be working with points. We're going to be working with values in the coordinate plane. Sometimes it's called the rectangular plane. Sometimes it's called the Cartesian plane. Sometimes it's just called the XY plane. It just means a graph. All of those things mean the same thing, the square one. We will do a non-square one in the spring. We'll get there. Okay, so the first thing we're going to do, just to kind of reorient ourselves with the coordinate plane, is we're going to figure out the set of points that would meet this situation. What would these things look like if we think about them in terms of a graph? So if we think about x equals -2, and you can sketch it, or we can like just think it, or we can kind of describe it. What would x equals -2 look like if we wanted to graph that? A straight up and down line. My x equals -2 means I would be stuck right here on -2. It is a vertical line through, usually we pick a point. You can pick -2, really anything, any y. I'm just going to pick 0 because it's there. It's a vertical line through -2, 0. It's a vertical line through -2, 3. It's a vertical line through -2, anything. It's just a vertical line. Yes, dear.
Do you have any of the sticker graphs?
Or like, yeah, these ones. I don't have stick ones.
I remember.
I was going to say, I have a couple of the Post-it ones, but not many. All right, what would something like y equals 3 look like? A horizontal line. You could do a horizontal line through any point on 3. So you could call this a horizontal line. Through any point that has a y value of 3. So you could say 0, 3, I could say 1, 3, I could say anything. Anything that goes through point 3. Sometimes if you're looking, especially at things like answer keys, sometimes the book will word it in a slightly different way, where they'll say, it's not that it's necessarily a horizontal line, but it's a line parallel to the x-axis. It means the same thing. But sometimes the book will write it in weird ways. So we could also say, or parallel to the x-axis. Both of them are correct. It doesn't matter to me which way we do it. Parallel to the axis through 3. And again, I'd pick a point through 0, 3. Or 1, 3. Or 5, 3. Or 10, 3. Or 100, 3. Generally, we pick something that's on our graph. So you don't have to sketch them. Sometimes it will help to kind of see what's going on. But not always. Sometimes we can do it with just thinking it. And it doesn't really matter how you describe it. As long as you are describing it accurately, I can work with whatever you got, however it's working for your brain. So whether it's a horizontal line through something 3 or a parallel line or parallel to the x-axis through 0, 3. Sometimes they'll give us weird like inequality situations here. So if we want to know where x is greater than 0, where do we have points that are going to have x greater than 0? On the right-hand side of the graph. All of these points over here are going to be where my x is greater than 0. So it's going to be all the points in quadrants 1 and 4. Because this guy's quadrant 1 and this was quadrant 4, IV.
Did you say like to the right of the y-axis?
Say that again?
Could you say like to the right of the y-axis?
Yeah, I take that too. All the points to the right of the y-axis. Absolutely fine. And they start to get a little bit weirder. D is a little weird. So if we want to think about where x times y is going to be greater than 0. Yeah. We need them to have the same sign, really, because if I have a positive and a positive, I'll have a value greater than 0. And if I have a negative times a negative, I'll have a value greater than 0. But if I have one negative and one positive, then I'm going to wind up with a negative number. So if I need my x times y to be greater than 0, that's going to be the values in quadrant 1, where we have a positive times a positive, or the values in quadrant 4. Sorry, 3. My brain stopped there for a second. Quadrant 1 and quadrant 3, where we have those signs that are the same. So it would be all of our points in quadrants 1 and 3. Because here we'd have negative times a negative. Our x's are negative and our y's are negative. And a negative times a negative is still going to be a positive. So these inequalities a lot of times are going to wind up with a quadrant as our answer, or more than one quadrant. All right, we have one more to look at on here. We've got our y less than 0. Where are we going to have y less than 0? Quadrants 3 and 4. Yeah, or anything below the x-axis. That would also work too. Just since we had that thought earlier. Our quadrants 3 and 4. Anything below the x-axis, that's where our y values are negative. If it helps you sketch it out, like 100% okay to sketch it out. Say my y value is negative, that's all the things down here. So that's all these guys. And we go 1, 2, 3, 4. So quadrants 3 and 4, below the x-axis. Anything where my y is negative.
Could you put all points in quadrants 3 and 4?
You can put all points in quadrants 3 and 4. Absolutely valid. Sock is falling off. There we go. Okay, so if it says something like this, describe the set of points that satisfy the given condition, just describe to me where they are. It just is an overcomplicated way of saying, where is it going to be? Okay, so thinking through our coordinate plane. The next thing we're going to talk about here is going to be the distance formula, which is something we should have worked with before, but it's been a minute. The distance formula is very much based off of the Pythagorean theorem. We just tend to write it with our pieces. So if we have 2 points where we're going to have point 1, so we'll have our x1, y1, and we're going to have another point, we'll call it 2, x2, y2. And we want to find the distance between them. The distance is going to come from the square root of the change in the x's. So we usually do our x2 minus the x1. And we're going to square it. And then we find the change in the y's squared. So we'll have our y2 minus y1 squared. So it's the change in the x's squared, the change in the y's squared. We sum them, And then we take our square root. It's very, very, very much based on the Pythagorean theorem. It's just been solved for C, basically. Look at our C equals. So we're going to use 2 points to be able to find the distance between them. So, first thing that's going to happen is I'm going to give us 2 points, and we're going to find the distance between them. So I'm going to give you guys a second to write down this formula, because we're going to need to have it. And then I'm going to give us 2 points. So give us a second. All right. So if we want to find the distance between -3, 6 and 5, 1, we're going to use that distance formula. So I'm just going to write the distance formula down here again. So in case we don't have it, we're going to have our distance equals the square root of the change in our x's squared and the change in our y's squared. It doesn't matter which one we choose as 0.1 and which one we choose as 0.2. I'll go ahead and call this one my 0.1. So I'll have A be point x1, y1, and I'll have B be point 2. So this is my x2, y2. It does not matter which one we have be 0.1 and which one we have be 0.2. We'll get the same answer either way. So we're going to substitute the pieces in that we know so that we can try and find our distance. So we're going to have our x's. I'm going to take my 5 minus the -3. And the change in our y's, where we're going to have our 1 minus our 6. And then we're going to simplify this. So our distance we're going to get, we're going to have 5 minus -3. What is 5 minus -3? Yep, so we get 8 squared plus 1 minus 6, -5 squared. What is 8 squared? 64. What is 5 squared? 25. And -5 squared is the exact same thing as +5 squared, +25. That is part of the reason these are squared, is it keeps those values positive. Our distance is always going to be positive. Distance will not be negative. I can't go a negative amount of feet. I cannot take negative steps. I cannot travel backwards in time. I wish I could, but I can't. So we can simplify this a little bit more. Square root of 64 plus 25, we're going to get 89. So I could, just kind of type this in the calculator to figure out where this is to get an estimate for it. To get a decimal, I could figure out that this is, somewhere between 81 and 100, which would be the two perfect squares that I know. So it's probably somewhere going to be between 9 and 10. It's a little closer to 81, so it's a little closer to 9, square root of 9. But it's not a huge deal. We get to use calculators, so it's not as big of a deal. So when it says in the book, if we're going to try and make an estimate, we can use a calculator for it. 2 years ago, we weren't allowed to use calculators in this course, so they had to be able to estimate it without it. So, lucky ducks, we get calculators. So, our square root of 89 is plenty. We could also simplify this. We could put it as a fraction, but it's, kind of a deal. That's what we're working with our distance formula. We can keep it like that, square root of 89. I could type that in the calculator to get a decimal version of it. Well, if we're looking at distances and we're trying to figure out which one's farther, it makes it easier. So this one's about 9.43. This is approximately equal to 0.43-ish. If you're looking at the yellow calculators, just because a lot of times with the square roots, it will try really hard to simplify them for you. Oh, it's thinking still. Hello, tiny calculator. So on these ones, if we do our square root of 89, it's trying to simplify it first. So if you want to switch it to decimals, you hit the little 2 arrows right above it, and it will switch it into decimal form. So it will try and simplify things for you. Like if I do the square root of 32, it will simplify it and put it in simplified radical form for you. So that does our 4 square root of 2. It will do all that for us. But, you know, it's a good idea to think them too. Okay. Questions on our distance formula? It's mostly substitute, plug and chug kind of deal. Because what these are going to be used for a lot of times is they're going to give us more than 1 point.
Oh.
And we're going to see if we can figure out if this is a right triangle. So I'm going to pass you guys out some graphs so we can plot them up and look at them. So here we go. And I'm going to put those in other rows. So. There we go.
There it is.
Yeah, if you've got graph paper, that's totally fine. I'm just like, I know not everybody has graph paper. If you want them, use them. If you don't want them, totally fine. My feelings will not be hurt. I would just rather give you graphs if you don't need them than say, I wish I had a graph. So we want to be able to tell if this is a right triangle or not. So the first thing we're going to do is plot up our points. So whether you choose to plot them in and then glue it in, or if you want to glue it in first and then plot your points, just be careful. Sometimes those glue sticks make the graphs a little wet. So we're going to plot these points and we're going to see if it's a right triangle. What does a triangle need to have in order to be a right triangle? It needs to have a right angle. So if we plot up our points, our -1, -3. Ooh, fun. Is right there. So that's my point A. My point B is at the point 6, 1. And C is at the point 2, -5. Oh, I should be losing. So this one's point C, and this one's point B. So I'm going to connect those up. It's looking promising. Like this could be ish. We know it's supposed to have a right angle somewhere. Do we have the capability to find the angles on this without like a protractor?
What?
I was gonna say, finding the angle on these triangles is not awesome. What else do we know about right triangles? They have a perfect 90-degree angle. Oh, that's not what I meant. There we go. So it should have a 90-degree angle. But if I don't know how to get an angle measurement right now, without a protractor. What else do we know about right triangles? A squared plus B squared equals C squared. I do know how to find sides of a triangle. I can find the lengths of the sides. Side A is going to be this guy. It's the one across from the angle. Side B is this little guy here. And side C, that one's our hypotenuse. Ish, probably, maybe. The hypotenuse is always going to be the longest side. So whatever we get as the longest is going to be that. So we're actually going to find all three distances. I need to figure out the lengths of all three legs of this triangle to see if it is a right triangle. So we need to know the distance between points A and B. That's going to give me side C. So points A and B. I'm going to do capital A, capital B, because those are my points. Point A, point B. So to find our distance on that set of points, we're going to take our B, so we take our x's, we're going to have our 6 minus -1 and square it. And then we're going to have our y's, 1 minus -3 and square it. So the distance between points A and B is going to be the square root of 6 minus -1 is going to give us a 7 squared plus 1 minus -3 is going to give us a 4 squared. So what we're looking at here, our 7 squared is going to give us a 49. 4 squared gives us 16. And we get the square root of 49 plus 16 is 65. I'm going to make this just a slightly different size just so I can actually fit stuff on here. So we know that this is for our side C, the distance between point A and point B. This is our side C that we have on this triangle. Then let's find the distance between points B and C. That's going to give us our side A. We're going to find the difference between all three pairs. So we're going to find the distance between those points. And I have a tendency to just kind of write everything out, just substituting pieces in. So we're going to have our point C, which was 2, -5, just so we can see stuff. There we go. So my x's, we're going to take our 2 minus 6 and square it. And our -5 minus 1 and square it. And we're just going to be careful because 2 minus 6 is going to give us a -4 to square. And this is going to give us -5 minus 1, which is a -6 to square. And that's going to give us a positive 16 and a positive 36. So the length of this side, square root of 16 plus 36, is going to be square root of 52. And that's our side A. So now I have 2 of the legs of my triangle, or 2 of the sides. I'm not sure if they're legs yet. We got one more side to go. We need to do side B, which is the distance between point A and point C. And C. That's going to give us our square root. There we go, do my points. So my x's, we're going to have our 2 minus the -1 to square. And our y's with our -5 minus -3 to square. So that's going to give us our 2 minus -1 gives us a 3 squared. And our -5 minus negative 3 becomes a negative 2 to square. Because that's the same thing as negative 5 plus 3. And we're going to have our square root of 9 plus 4.
13.
Yep, square root of 13. So this is our side B. So we had looked at this before, and we kind of were looking at our picture going, okay, C definitely looks like it's probably the longest. But if we didn't sketch it, or if we didn't look at that, we could figure out square root of 13, square root of 52, square root of 65. That guy's definitely the longest. So if this is a right triangle, that's going to be our hypotenuse. The hypotenuse will always be the longest side. So to prove that this is a right triangle, we've got to check the Pythagorean theorem and see if it works. We want to know if our a squared plus our b squared is really going to equal our c squared. Is this going to be a right triangle? So if I take my square root of 52 squared, and we add our b squared, which is our square root of 13 squared, does that equal our square root of 65 squared? Which is part of the reason I didn't simplify these out of that radical form, because then those radicals just straight up all cancel out. So this is our right triangle test. Because we're just looking to see, does 52 plus 13 equal 65? Yes, it does. So this is a right triangle. Yes, it is a right triangle. Because the Pythagorean theorem holds. If the Pythagorean theorem did not work, it would not be a right triangle. Pythagorean theorem always works with right triangles. So if this works, we're a right triangle. If that does not work, not a right triangle. If we're looking at to see if something's an isosceles triangle, that would be when we have two sides exactly the same length and one side that's not. Equilateral has all three sides the same. And then we kind of skipped over it in the instructions up here. There is actually one more question they're asking us to do. They want us to find its area. Finding the area. How do we find the area on a triangle? Do anyone remember? 1/2 base times height. What is our base and what is our height? Yeah. The base is one of the legs, and the height is the other leg. Anything that's not the hypotenuse counts as our base and our height. Because we're on a right triangle, this will be my base and this will be my height. So we don't need anything special for it. We're just going to use those two sides. Our area is going to be 1/2 of our square root of 13 times our square root of 52. Well, that's the same thing as the square root, or 1/2 of the square root of 13 times 52, which is an unpleasant number. It's 676. But that is, in fact, a perfect square. Yeah, you're just like a half step into me. Yeah, because we have our 1/2. Our square root of 676 is actually 26. So this actually is going to equal 13. The reason that happens is because if you think about 52 being simplified, that's the same thing as if we had 4 times 13 times our square root of 13. So we can simplify this without a calculator. We don't have to do it in the calculator. That's okay. That's what I was going. That's what I was like. I wanted to look and see because I was like, I didn't want to be like, you're wrong. Okay. So sometimes they're gonna ask us to prove something, and like that's definitely a vibe. Okay. So we'll talk through the next thing, but we'll do most of the practice problems with this tomorrow. So this will be the last thing we kind of talk about. Because the next thing we're going to look at is perpendicular bisectors. So a perpendicular bisector is a very specific point. Or it's a very particular segment. And a perpendicular bisector is perpendicular to a segment and intersects it at the midpoint. So if we're thinking about a segment, I typically think about a segment like this. It'll be A and B. Our perpendicular bisector is going to go through our midpoint. I'm going to call that M. And what that means is that this piece and this piece are exactly the same length. That's typically how we denote that, is with a little like hash, a little tally. I'm going to fix that M. Just so that it's easier to see. So our midpoint is the halfway between, and our perpendicular bisector goes through M and is perpendicular here. So the way we're going to test that, and when we're going to look at perpendicular bisectors tomorrow, because that'll be where we start tomorrow, is looking at these perpendicular bisectors, is that no matter what, if we have a point that is on our perpendicular bisector, it is going to make two exactly congruent right triangles. Any point on this perpendicular bisector is exactly the same length from either of the end points. This segment is the exact same length as this segment. Any point on this piece is also going to be the exact same length between A and B. So any point on the perpendicular bisector is going to be exactly equal to A and B. So tomorrow what we're going to do is I'm going to give you 2 points and say, show that this point is on the perpendicular bisector. So we're going to find distances between lots of pieces. So we're going to be using the distance formula a bunch. So we have like 5 minutes, and so I don't want us to try and speed run it, but this at least gets our definitions down, and we're going to talk through we're going to work through some of these perpendicular bisector problems tomorrow. If you would like to see your test, I have those. Now would be a great time to do so because we have 4 minutes left in the period, and I don't want us to try and speed run a problem. So if you would like to see your chapter test, you're welcome to. I'm not going to make you look at it. I am going to put up our announcements with our first set of homework. Yep, I will put it back on this. If you would like to see your chapter test, come on up. If you don't want to, that is totally okay. All right.
Well, that and also I have to finish it anyways.
Cat, that's okay. Thanks. And Katie. Where are you? I don't know if you got stuck with this. Oh, there you go. Just stuck it on there. Come on, you want to see yours?
Is this 3D printed?
Yep.
It's a lot of texture.
Yeah. Well, it's partly because my filament is expired and I was using it up. I was like, you can't keep your tests. I do need to keep them, but you are welcome to look at them.
So it was 13. Okay,